Today we're going to start some new material, class, and we're going to start with one-way ANOVA. I know you did one-way ANOVA, but still there's some new material here. Now, I've written down in parentheses between subjects analysis of variance, because throughout this semester we're not going to deal with within subjects analysis of variance. So, like t-test, we have dependent ANOVA, or within subjects ANOVA, and an independent ANOVA, or between subjects ANOVA. So, throughout this semester, all we're going to do is going to delve deeper and deeper into between subjects analysis of variance, meaning that we're going to have several groups, and each group are going to be different individuals. Okay, so that's what we're going to practice throughout the semester. In the beginning of the second semester, we're going to go into within subjects. Okay, before we start the actual material, I've heard from some students that you were having problems with this formula, right? This is the independent sample t-test formula, and I've heard that you had a different formula last year. So, first of all, I've asked to send me the original formula one that you had, and if we'll see a need to bridge the two formulas, we'll do that, and if we'll need to do that to add the previous formula, we'll do that. I want to remind you that this is not a very mathematical course. We're not going to do a lot of mathematics, we're not going to do a lot of algebra. I know that in the homeworks you have to do, for example, t-tests from A to Z, right? Calculate everything from start to bottom down. But in the test, we're not going to do that. In the test, we're going to ask you to calculate something very simple in order to exemplify a theoretical point. Okay, so we're going to use the formulas as a subservient of the theory, not the mathematics itself. But nevertheless, I want to explain the formula because it's going to be a good bridge for today's lesson. So, when we conduct a t-test, and all t-tests are the same thing, we're talking about obtained difference versus difference expected by chance. So what's the obtained difference? It's the difference between the groups, right? We have group 1 and group 2. And this is expressed by m2 minus m1. What's m? It's the mean. The mean of group 1 minus the mean of group 2, or vice versa. Also can be expressed as x bar 1 minus x bar 2. Okay. So that's the difference between the groups. That's the main part. Now, this, we have like a small point about this one. Mu2 minus mu1. So these are the values that we expect to find under the null hypothesis. What is the expected difference under the null hypothesis? Now, usually we're asking, is there any difference? That is there a difference that is larger than 0? So the null hypothesis will say that mu2 minus mu1 is simply 0. We kept this part of the formula just to make the point that we can ask the question, is the difference larger than 5? Right? We can have the null hypothesis being that the difference between the groups is 5. And we're looking for something that's larger than 5. But usually that is throughout the course, this will be 0. So the numerator is simply the mean of group 1 minus the mean of group 2. Okay, that's the obtained difference. Now the bottom part is the trickier part, right? We have SS and SS. I know that last year you didn't talk about the sum of squares up until we talked about ANOVA. But the sum of squares is simply a form of a measure of variance. There's nothing magical about it, right? It's just a form of variance. So we have the variance of group 1 and the variance of group 2 divided by the combined degrees of freedom, multiplied by this number of subjects. And the point is not to understand it completely. The point is to understand that the difference expected by chance is a sort of pooled, it's a pooled estimate of variance. Right? We have variance from group 1 and variance from group 2. So together we're pooling the variance from both groups and we're creating a new estimate of variance. And from last week we had a slide explaining why is that so. Why is the variance of the sampling distribution directly connected to the variance of the individual samples? Okay, so basically the theoretical point here is that we have this obtained difference versus difference expected by chance, meaning that we have the differences between the averages versus this estimated standard deviation of the sampling distribution, which is based on both samples. Okay, before we start, does anyone have any question about this formula? Again, it's not about the formula itself. We know that you can plug in numbers, right? We're not concerned about that. What we do want you to understand is the theoretical point. Now, here is today's story. A researcher team were interested if there was difference in the quality of wine produced by wineries based on their country of origin. So this is an international course. One better way is to compare different countries and say who's best. They sampled 3 wine manufacturers from Brazil, China, and the UK. So we have 3 wine manufacturers from 3 countries, so 9 observations. Each winemaker produced 1 bottle that was rated on a scale of 100 to 250. So we want to compare 3 groups. Of course, 3 individuals in each group is not enough in any real study, but we're doing this so we can actually see the calculation in action. It's going to be easier for us. But we have 3 groups. Can we compare these groups using a t-test? No, because a t-test is meant for 2 groups, right? So there's no way to use the t-test in order to do this comparison. Of course, when we have more than 2 groups, we have to conduct an ANOVA. So we're going to conduct a between subjects ANOVA. Now, the first thing I want to talk with you about is difference between groups. In ANOVA, we ask basically the same question we asked in the t-test. Is the obtained difference that we found occurred due to chance or due to a real difference between the groups? In other words, we ask, did all the samples come from the same population, or did they come from different populations? The null hypothesis will say all the groups are exactly the same, right? There's no difference in the wine quality, either in the UK, the China, or I don't know about Brazil. The researcher's hypothesis is that at least one of the groups is different. Right? There is some kind of difference. Now, what's the difference between groups? In t-test, it's very clear, right? No difference between the groups, just the difference between one average and the other average. It's just a subtraction, it's a difference between them. But what's different between groups when we have 3 groups? So difference, I told you before, when I say difference, I can just switch the word and say variance, right? Or another way, when I say variance, what I mean is difference. So instead of saying differences between groups, I can ask what's the variance between the groups. So I want to appeal to your intuitions. Which situation is better from the researcher's point of view? The researchers want to show there is some kind of difference. That's interesting. So which is better? This is sample A. And what do we see here? We see the infographics here is that the taller the bottle, each bottle is one individual observation. The taller the bottle, the higher the quality, right? So this is a measure of quality from 100 to 250, and we have 3 bottles in each sample, right? We have okay, China, Brazil, okay, and this is what we got. Non-observations and sample number 1 we got. The average score was 179, sample 2 was 180, and sample 3 was 181. Is the infographics here clear? Which is better, sample A or sample B? What happened to sample B? Now, instead of 179, 180, 181, we got 170, 180, 190. So here, the difference is this, and here the difference is this. Which is better from the researcher's perspective? It's sample B. Is it 50? Okay, so here we have sample A, a very small difference between the groups, right? It's intuitively we can see that in sample B we have larger differences. We didn't calculate it yet, but we can see in our eyes, even see the average here is very similar to the average here, and it's very similar to the average here. And here there's larger differences.
She's asking what's better in terms of what is better.
Okay, good question. So what are we asking? We're asking, is there any real difference? Right? And the larger the difference, the easier it for us to say, yes, there is a real difference. Remember the stupid example I gave you with the island of Cyclops, right? There's an island of people with just one eye. And there's a boat coming in, and all the people on the boat have 2 eyes. And we ask, is there a difference? Did this sample come from this population? No, all of these people have just one eye. So the larger the difference between the groups, the easier it's for us to say, right, there is a real difference. It's not just a chance occurrence that we found in our samples. Right? This difference, of course, we'll find some kind of difference. We'll always find some kind of difference. Think about it. What's the chance that in this story we have 3 wine manufacturers in each country, and we sample the bottle and we give them an average score? What's the chance that the average will be exactly the same in all 3 groups? Right? There'll always be some kind of difference. Well, let's say I'm looking at difference in heights between this class and the other class. I think they're studying economics or something. And I sample everyone. Okay? Now, of course, there's going to be some difference in height. It doesn't mean that there's an abstract rule governing this difference. Right? We're looking for a real difference, not like a difference that occurred by chance. So the first intuition I want to give you is that a larger difference between the groups is better for us. It's better for the researcher trying to prove that there is a real difference between the groups. Okay, that's the first intuition. Any questions about that?
Between groups of the same sample?
So we have a sample of people from the UK, from people from China, and people from Brazil. So we consider it like 3 samples. Okay. So the larger the difference between the groups, the more assured we are that there is an actual difference. Right? That's, for example, the example of the NBA players versus regular people. It's very clear to us that NBA players are different from the regular population, right? Because they're so much taller on average than the regular population. Like in a t-test, we compare the obtained difference to difference that is expected by chance. So we got an intuition about what's the obtained difference. Now let's get an intuition about what's the difference that is expected by chance. Now this is again sample B. And we say that the difference that is expected by chance is based on the difference within the groups. Right? Difference within the groups. Now, do you think there's a lot of differences in this group? They're pretty similar, right? The wine from UK is very similar to the wine from UK. The wine from China is very similar to the wine from China. The wine from Brazil is very similar. All got almost the same grades. So this is sample B. Now look at sample C. So again, look at the screen. Sample B, small differences within the groups. Sample C, large differences within the groups. What does that mean? For example, in sample 3, right, the Brazil sample, we have one wine that was so good, it got a 250. Okay, but other wines have got 180, right, 190. There's a large difference within the groups. Now, what if I got this wine by chance? Right? From all the wines and wineries in Brazil, I got this one wine that's particularly good. Not really a good representative of Brazil. But because of this one, my average got skewed upwards, right? The only reason why I have such a high average is due to this one wine. The only reason why I have such a low average is due to this one wine, right? Here, everyone, sample B, are consistent. I got 3 examples, and all these examples are consistent. In sample C, the sample is really not consistent. Now, I don't know about you, but think about the possibility that only this one observation is the only reason why I got the difference between the groups. Scares me. I don't want this as a researcher. I want to see a real difference, not something that occurred because of this one random sample. So, because I want the results to be consistent, I don't want a lot of differences within the groups. So, is it clear that the intuition that for us as researchers, sample B is somewhat better than sample C? The averages are the same, right? Differences between the groups are the same. But in sample C, there's larger differences within the groups.
So which one is better?
So, B, small differences within the groups. All the samples are consistent, right? In sample C, large differences within the groups. The samples are inconsistent. There's a lot of noise, a lot of chance here. Okay. So, again, appealing to your intuition, I want to say that as researchers, we want small differences within the groups. When we have large differences within the groups, we don't know what it means. So, the difference within the groups is the difference that is expected by chance is evaluated based on the amount of within group variance. So this within group variance represents our statistical noise. The more variable the samples, the more likely to get large differences just because of chance. Just because I sampled this one wine that was particularly good or particularly bad. And again, here, this seems convincing that this average really represents the wine quality of the UK. Think about it not as three observations. Think about it as 30 observations. Okay? And all the observations are around the 170. And in China, all the observations are around the 180. Right? There's very small differences. And then think of this one. and the observations are all over the place, right? And then a difference of 10 points. What's the difference of 10 points if the scale is all over the place? Yes?
The slide with the text or the next one.
Yeah. Okay. I also want to remind you that this is exactly the same thing as we said in a t-test, right? Independent sample t-test. The larger the variance in each group, right? The larger the difference is, the less likely that our result is a real result, or our difference is a real difference. We talked a lot about it in lesson number 2 and lesson number 3. Okay, so that's trying to appeal to your intuitions. We want large differences between the groups, but small differences within the groups. About the t-test? This one. Within group variance represents the statistical noise. So we'll get there. The more variable the samples, the more likely to get a large difference between the groups by chance. So that's what I tried to say about this one. Right? I'm asking, why did we get this result? Does this result and the difference between these two groups, does it represent a real difference, or does it represent just a chance occurrence? So think about it. The only reason why I got 190 here is because of this one sample, one observation.
There are differences.
Within the group. Right. I'm saying that here, I can't really rely on this difference. I don't know why. Is this difference a real difference, or just because of this one observation? But I'm sure we'll get there as well when we continue to get a bit clearer. Yeah?
So the denominator in z-test, t-test, whatever you're doing, is always representing the within group difference.
Right. Basically, yes. In all the tests that we did so far, we've got obtained difference versus difference expected by chance. Now, in each test, the difference expected by chance is calculated a little bit differently.
It's calculated based on the variability based.
Right. But here, the variability is based on differences within the groups. Okay. So, when we conduct an ANOVA, we calculate an F statistic. The F statistic represents obtained difference divided by difference expected by chance, right? As did all the statistical tests that we've done. And the obtained difference is basically variance between groups. Right? Instead of saying differences between groups, I'm saying variance between groups because differences and variance is essentially the same thing. Large differences mean large variance between groups. And the differences expected by chance is evaluated by the variance within the groups. Okay. Let's see how we calculate all these components of variance. If anyone has any more questions, please feel free. I do assure you that we're going to be clearer and clearer as this lesson goes. So far, it was just an appeal to intuition. This is an interesting question. What would happen if there was no differences? This is supposed to be within the groups. No differences within. Just a sec. Correct that. If anyone has it written down, please correct this as differences within the groups. So let's say all the differences there's no differences within the groups at all. Right? All the bottles I sampled from the UK are all the same. All Charles I sampled from China, all the same. Okay. Absolute consistency within each sample. So now I'm going to ask, which of these is more convincing? Now the intuition will be to say that sample D here is more convincing than sample E, because there's large differences between the groups, right? Here's the average is 190, 180, 170. There's large differences between the groups. And here there's such a small difference. This is supposed to be 179, not 171. But here's a small twist. Again, I told you before, we're not asking, are there large differences? We're asking, is there any difference? Is the difference between the groups larger than 0? So we're not trying to evaluate the size of the difference. We're just asking a modest question. Is there any difference between the groups? So if there's no statistical noise, if there's no source of difference expected by chance, any difference will be considered as a significant difference. So in this case, a very extreme case, of course, when there's no within group variance, any difference is considered equally significant. So regarding the question, is there any difference between the groups? In both samples, the answer would be yes. Even if the smallest difference will be considered significant if there's no variance within the groups. So this is a bit of a tricky point, okay? But it educates us to what we're asking in statistics. We're not asking about, is the difference larger than 10? We're asking, is there a difference that is larger than 0? Okay, any questions about that? Was it clear to this point?
Sure.
Because this is a tricky one. Okay. Good. So how do we evaluate the different variance components? We want to calculate both the variance between groups, which represents the obtained difference, and variance within groups, which represents difference that is expected by chance. Before we start calculating these different components, I want to remind you what's SS, what's the sum of squares. And again, I told you before, I don't want you to see SS and keep it in that level. I want you to write a dictionary. I want you to understand it as the sum of squared deviations from the mean. So in order to calculate the variance, I'm not going to see the difference between one bottle and another, and another bottle and another, and another bottle and another. What I am going to do is choose one measure of central tendency, the mean, the average of the group, and I'm going to check the differences between this average and each individual observation. So, sum of square deviations from the mean, we have a single observation minus the group's average. So here's the group average. Okay? If you haven't seen the animation, look again. We have these 3 observations, and then we have a group average. Okay? So this is not an actual observation. This is the group's average. So we look at x minus x bar. That is the difference between this observation, right? This 140 minus 170. All clear about why did I look at this difference? So 140 minus 170. We got minus 30. And then we do it again. 150 minus 170, minus 20. And then we do it again. 220 minus 170. So these are all the differences between each individual observation and the group's average. And then this sigma, right? Sigma, again, Greek letter doesn't say a lot. We need to translate it into the sum of. So the sum of, but we won't just summarize these deviations, we'll summarize the square deviations. Yes?
You said again the difference between the groups, what?
So the difference between a single observation and the group's average. What would happen if we just summarize these three differences? We get minus 30 plus minus 20 plus 50. We get 0. Okay? That's the rule of the average. If you summarize all the differences from the average, you always get 0. So we can't do that. What we can do is summarize the squared differences. So the sum of squared deviations is this. Okay, we got SS equals 3,800. What does that say? Not a lot, basically. Okay? The only thing that we know is that the larger this number is, the more differences we have in our group. Okay? More differences we have in this group. But we don't know what it exactly means. Right? We can't really translate it to people. Oh, I got an SS of 3,800. Is that a lot? We don't really know. Okay. This is the meaning and idea of sum of squares within a sample. Questions? Right, relatively easy. Okay? Do you understand why this measure represents differences? If there were no differences, SS would be equal to what? 0, right? Because everything will be exactly on the mean. Okay. So now, based on this idea, we can understand what is the sum of squares within the groups, right? The first component we want to calculate is the variance within the groups. So what do we have? We have a single observation within a specific group. First of all, this is really, seeing this will just give you a background, right? Without understanding what it means. The meaning is so simple, but just looking at the formula without understanding it, it's just what's xij, what, and x bar j doesn't mean a lot. But if we work slowly, we can see it actually has a very straightforward meaning. So we're looking within each sample, a single observation minus the group average. So if we have the sample of the wine from the UK, we can calculate the sum of squares of this individual sample, right? We have a single observation within this specific group minus the group's average. Okay. And we already know that the sum of squares for the UK wine is 3,800. Right? We already calculated that in the previous slide. So now I'm not just going to say this is the sum of squares. This is the sum of squares for group number 1, right? SS1. But we don't have only one group, we have 3 groups. If you're not looking at the screen, you're missing all my beautiful animations. Again? Hoppa. So we have three groups. The same process we did in the previous slide, we can do now for each individual group. Right? So we can calculate the sum of squares in the China sample, and we can calculate the sum of squares in the Brazil sample. And each group will have its own sum of squares. So, SS within, or in other words, SSW, is simply the sum of these. You take one sample, you calculate the sum of squares. You take the other sample, you calculate the sum of squares. You take the third sample, you calculate the sum of squares. And then you summarize all these sums of squares. Sum of square within the groups is literally sum of squares within group 1 plus sum of squares within group 2 plus sum of squares within group 3. So we get that SSW equals, in this case, to 7,800. Is this process clear? Is it clear why this is sum of squares within the groups? Like we keep looking within the groups. Okay, that's SSW. Yes?
I'm not sure I understand why you add the sum
So this sigma, whenever we see a sigma, this large sigma, it means summarize. Summarize what's in front of us. What's in front of us? Single observation within a specific group minus the group average. So think about a computer program, right? Going through observation to observation. And it says, okay, we have this observation. What's the group's average? Okay, next observation, next observation. Summarize that. Then go onward. Next observation, next observation, next observation. And the function, the algorithm, keeps summarizing. So eventually what will happen is that you're going to summarize all of these, and then all of these, and then all of these.
But at the level of interpretation,
Yeah.
like I understand the interpretation, but when you're interpreting the numbers, what does a large number like this mean? Like, don't you, how does it tell you, what if you have many of these large variants in one sample, but really small in another? Like, does the average give you those constant?
Right, that's a very good question. Okay, so I don't want to focus a lot on it, but I will say this. Remember in independent sample t-test, we have an assumption of equal variances, right? We never get exactly the same variance within each group. There is always some difference. But if you get, let's say you got 10,000 here and 300 here, it means that there may be a violation of that assumption. If you get huge variance in one group, but almost no variance in the other, maybe there's a violation of the assumption of equal variances. And that's a problem. There's all kinds of different ways to deal with that problem, but it is a problem. Okay? But if we do assume equal variances, it doesn't matter that we have these slight differences, but because what we want to see is a pooled measure of variance. What else?
No, I didn't understand the assumption of the what variances.
Okay, so last year and also in the recitations, we talked a little bit about in the independent sample t-test, you have an assumption of equal variance. This means that the variance in the first sample is supposed to be relatively the same. The amount of variance is supposed to be the same. What's the violation? That rule is, for example, if you have this versus that.
Oh, when you change it.
Yeah.
When you multiply it, you add or multiply or whatever you program.
So we won't deal with it in the formulas. So first of all, the assumption is important to us because the tests are designed using this assumption. If you have a violation of the assumption, the tests become a little bit less valid. It's not really part of the course material, if you will. What? Okay, so what we're saying is, because we assume people can make sense, we don't mind that we have a different amount in each group. Because what we're saying is, okay, we got this small difference, but basically they represent the same thing. Okay, yes.
So these aren't considered so extreme, 30, 140, 140.
Right.
These are not, what are
Right.
considered extreme numbers where you really can't.
Extreme differences.
Extreme differences, yeah.
So, a rule of thumb will be that if you got 5 times more from the lowest sample to the highest sample, like that will be an extreme difference.
And we can't assume variances in that case.
Yeah, but we're not going to focus on that. Of course, this is just something that you can know. But basically, you'll have just a test to test the assumption.
Yeah, the means test.
Yeah.
But theoretically, like, why is it it's not a problem? I understand, okay, it's like close to gate 410, but why this is, you said like it more like represents the group essentially, like when you're not, when it's not so extreme. So what do you mean by that? Like these all represent what, like variability wise?
So so that's the last thing I'm going to say about that, and then we'll continue. When we say variance is expected by chance, we think that there's an actual measurement that can represent chance, right? There's a real thing that we're trying to get to. Now, we won't ever know that we're there, right? But we have an estimate of that. In t-test and z-test, it's more simple because you had sigma, and then you have S, which evaluates sigma. So this is the very best approximation we have to this number. Variance is expected by chance. Okay, moving on, because I think I lost some of you. It's okay, it's fine.
You're
It's
saying
fine.
we have a limit of what we can make up by chance. Saying once it goes past that limit, then we can't do the assumed variability.
Yeah. Okay. Now let's talk about sum of squares between the groups. The obtained difference. Now again, looking at a simple difference between groups, group number 1 minus group number 2, is also a form of variance. So when I write something like this, right? This difference between groups x bar 2 minus x bar 1, I'm actually talking about differences between groups. Now, because in this case, I don't only have 2 groups, I have 3 or more, what I'm going to do is calculate sum of squares between the groups. I'm going to apply the same method to the groups. So what do we have? We have x bar j. X bar j. So the mean of the first group, or the mean of the second group, or the mean of the first group, or third group, minus m, this capital M. This will be the grand mean. The mean of all the observations, the mean of all the groups. So, what does it mean? So the first thing, does anyone see in this formula a representation of the single observation? Do we care about the single observation in this case? No. So what can we do? We can make them go away. Okay. Next step, we have these 3 averages. We want to put them all on the same scale. 1, 2. Okay? If you're losing all my beautiful animations, just look at it in the PowerPoint afterwards. It's worse there. So we have these 3 groups. And each number here represents the group's average. Now, I'm going to want to check the differences between them. So I'm going to need the grand mean. Okay, now look, this is not a scale of observations anymore. This is a scale of group averages. So, X bar of the first group minus the group's mean. So we get 170 minus 180 squared, of course, right? Minus 10 squared plus 0 squared plus 10 squared. So what did we do? We calculated the sum of square deviations between the groups. We're looking at each group average as if it was a single observation, and then we're looking at the average of these observations. Okay, again, we're looking at each group, okay, and we're asking what's the difference between this group's average and the grand mean. So here it's minus 10, here it's 0, here it's 10, and every time we square it. Sum of squares is a. So the next step will be to summarize them. But, there's a small but. Look at this number, right? This n. Number of participants in each group. So this means not only we have to summarize the square differences, we have to summarize this, right? 3 times 10 squared plus 3 times 0 plus 3 times 10 squared. Why 3? Because each average represents how many people? 3 people, right? 3 bottles, basically. 3 observations. It is clear at this point? Each average, let's see from the beginning, right? Each average represents 3 bottles. So when we continue, the number of subjects or observations in a specific group is the number of participants on which the average was based. And we get this number. SSB equals 300 plus 0 plus 300. Who can give a guess? Why do we need this multiplication, like times n?
Because if they have different amounts of people, they need to weight it.
Also true. That way, we can say that if we have an average represented by 100 people, and an average represented by 10 people, it will have different weights. Right? But there's one more reason. So, what do we do in statistical tests? We compared obtained difference versus difference expected by chance. Now, the difference expected by chance, SSW, was based on single observations. But SSB is based on group averages. We want to bring them to the same scale. Right? Think about it. This SSB, let's say it's not multiplied by the number of subjects. This SSB will be the same if we're not multiplying it by n. If we have 3 people per group, or we have 1,000 people per group, right? But SSW will just keep getting larger and larger and larger and larger, right? If I have 1,000 people in each group, SSW will not be 7,000, it will be 700,000. But SSB will remain this small number. It seems unfair, right? Unfair because we need them to be in the same scale. So the way we adjust SSB to be in the same scale as SSW is by taking into account the number of participants in each group. So now it's a fair game. Now we have an estimated variance between the groups and an estimated variance within the groups. Any questions about this process? I'll say it like this. The more participants we have, the larger SSB. The same difference between the groups will be considered larger if it's represented by more people. Right? Think about it this way. If you sampled the entire population and you found no difference, there's absolutely no difference. SSB equals 0. But even if there's a slightest difference, SSB will be huge because there's a slight difference, but based on the entire population. And again, because this is just because we're trying to see, is there any difference between the groups? Okay, we can continue, I think. One more thing is the total variance. One less formula, the least interesting of them, but it makes a point. So what do we have? This is the SST, sum of squares total. Xi, that is a single observation, minus the grand mean. So what are we doing here? Again, we're calculating sum of squares. But we're considering now not each particular group. We're not interested in the variance within group 1, within group 2, within group 3. We're interested in the variance in all the observations. So in other words, we're considering all the observations as one sample. So look at the previous animation. All the observations are one sample. And from this point, it's the same formula as the original sum of squares, right? What do we do when we have one sample? We look at all the individual differences. 140 minus 180. 150, 180. It's supposed to be 180. 160, 180. 170, 180. So on and so on and so on. Now, the SST is not really interesting. Why? First of all, we don't need SST in order to calculate the F-test. Right? All we need is to obtain difference, and the difference is expected by chance. So SST is irrelevant when we conduct this inferential statistics. Another reason why it's not really interesting is that we don't really need this calculation in order to find SST. That's because that if we summarize SSB and SSW, we get to SST. So think of it as a variance as a pie, okay? Pie chart, but think about it as a pie. So we have this variance, this pie of variance. All the variance in my samples is represented by SST, total variance. And this pie gets cut into two parts, to SSB and to SSW. The explained variance and the unexplained variance. Okay, SSB, variance between the groups, is variance that is explained by the difference between the groups. Right? That's what we're trying to explain. SSW, variance that is expected by chance, is variance that I don't understand. What does that mean that I don't understand it? I want to go back, way back to, okay, let's say this one. Okay. I can ask, why is there a difference between the groups? Why is there a difference? Maybe it's because there's a real difference between the groups. This is something I'm trying to explain. But if I ask you, why is there a difference within the group? Why? Why is there a difference within the group? The answer will be, well, just because. Right? Because there's differences, we don't know. We have no tool to evaluate why is there a difference within the group. So this variance within the group is variance that I can't explain. Not by anything other than saying, well, it's chance, it's randomness. Yeah.
It's just that people are a little bit different.
Yeah, but there's no governing rule behind it, right? Just saying, yeah, people are different. It's not a really good explanation, right? So why did this drug work? Well, people are different. It's not. It's the non-explanation. Okay. Okay, so I'm going back. That's not. Okay. So, two things in this slide. First of all, there's no need for us to conduct this calculation. You should never go, unless there's no other data, but you should never use this formula. Why not? Because this rule always applies. Total variance equals to SSB plus SSW. In other words, there's this high of variance. Some of it is variance that I managed to explain, meaning it's explained variance. Some of it is variance that I couldn't explain, meaning unexplained variance. And that's something that's quite elegant, right? We have this I, some of it is explained, some of it is unexplained. Any questions? I'm wondering if you're all understanding it or all not wanting to ask me the questions. Okay, I think I'll continue. Is it clear if I ask you now, if I give you, okay, here's something I'm going to do in the test. Okay, we can give you SSB and SST. Obviously, you also have this in the formula sheet. Okay, so if you have SSB and SST, of course, you can also say yes. Want to ask? No. So if you have SSB and SST, of course you can get to SSW. Right? Simply because total variance minus unexplained variance gives you explained variance. And total variance minus explained variance gives you unexplained variance. What do you think? Is this impressive? 600 out of 8,400? Not a lot, right? Now we can also already have like a feeling about data. Okay? Before we just had unexplained variance equals 7,800. What does that mean? It doesn't mean anything until I have something to compare it to. Yes, well that's.
Yeah, I just wanted to clarify. What would happen if we were to add participants, which would create more variance within, then the total variance would necessarily get bigger and would not necessarily affect the between in any direction. Is that correct?
Yeah, but you can also have a situation where, let's say you're adding participants which are exactly the same as the group average.
Yeah,
But then it didn't increase SSB, but not SSW.
But not SSW.
Right? If you add only participants that are exactly the same as the group average, you increase SSB. Sure. You increase SSB, but not SSW.
And if we realize, for example, oh, we made a mistake, really SSW is smaller. Well, it will always necessarily affect. If SSW is smaller, SSB is larger, and vice versa?
Yeah, okay, so this is a good point. Okay, there's a seeming dependency here. It seems that the larger SSB is the smaller SSW, right? Because there's this neat pie going on. But SSB and SSW are independent. Unless I tell you, let's assume that SST is 8,400. Once we know the size of our pie, all we can do is cut it in two pieces. But otherwise, if you have larger SSB, SSW can be small, can be large, just will increase SS.
Depending where the participants are,
Yeah.
where they fall in the
Yeah,
Both of them together.
yeah, exactly. Depending on where the participants fall. I can have a situation where I add participants and SSB will increase, but SSW will not. And I have a situation where I add participants, SSW increases, but SSB.
or they will both increase. No?
Right.
No. Okay.
Two things you can't do when you're trying to calculate SSB, SSW. The one here, there's one you cannot do. You can't infer one from the other. What was that?
They're independent.
Not saying
Unless-
essentially there was one particular, like, if you have an SST, like, there's one particular one you can't draw one from the other. Like, it's not dependent.
Yeah. It's, okay, so in a question, in a test, right? If I tell you the size of SSB, obviously every point of SSB is taken from SSW, right?
If you draw SSB and SSW from SST.
Yeah, exactly. But if you don't know SST, you can't conclude about the size of SSW from SSW, right?
And vice versa.
Yeah, of course. They're completely independent. Okay, moving on. This is the ANOVA table. Okay, I've probably seen it last week, right?
Yeah.
Now, this table gives you all the calculations you need in order to get to your precious F. Right? We started off wanting to calculate F. That's our statistic. Instead of calculating T, we're calculating F. Now, you're going to have the sum of squares, which we worked on now. Afterwards, you're going to have degrees of freedom. Now, each component has different degrees of freedom. Degrees of freedom between is k minus 1. What's k? K is the number of groups. In Hebrew, it's easy to remember. You just say kfutzot. Kfutzot is the Hebrew name for groups. So k, the number of groups we have. How many groups? 3 groups, right? So k minus 1 equals 2. Degrees of freedom within n minus k. How many participants we had in the entire sample, right? In all the samples. So we had 3 participants in each group. We had 9 participants overall. So 9 minus 3. MS. So what's MS? M stands for mean. So MSB, the mean of the sum of squares between the groups. MSW, the mean of the sum of squares within the groups. So MSB and MSW is simply taking the original SS component divided by the degrees of freedom. And finally you get to F. F is the MSB divided by the MSW. Now, of course, this entire thing is in your formula sheets. Of course, you don't need to remember. Okay? But the kind of questions we can ask in the test, there's at least one question like that. We'll give you some of the information in this kind of ANOVA table, and you'll have to fill in the blanks. Okay? In the recitations, you'll practice that. Sort of simple algebra work. So in our study, we got these three numbers, okay, 600, 700, 700, 800. We got 2 degrees of freedom between, 6 degrees of freedom within. Okay, remember this number, 2 between, 6 within. And then we get that M is 300, MSW is 1,300, and then we get F that is very, very small. F equals 0.23. What does this mean? Well, still not a lot, because we have, so far, we did all the calculations that we needed. Now we're going to have to make a decision. Yes?
What does N and K stand for? Because one's the mass population.
So N is the number of all the observations. K is number of groups. K groups. Don't have to remember that anymore. So we did all the calculations. Now here's the final point where we make our decision. What's the decision? Now we're doing inferential statistics. We're using our sample in order to infer about the population. Right? We're doing this magic trick of describing our sample, looking at it, and then using this statistic in order to have a conclusion. How do we do that? We're looking at the critical F value. FC, the critical F value, with 2 degrees of freedom between and 6 degrees of freedom within. So dF between, dF within. Now you did it last year and you're going to do it in the recitation as well. You have the critical F table, and from these numbers you're going to have to look for the accurate critical value. So you have to look at this number as the number of columns, and this number is the number of rows, and then you're finding that this is your critical value. Yes?
I noticed that the F table doesn't have, after 30, it doesn't have every degrees of freedom for within. So do we round up or down? Do we make it more difficult for ourselves? What do we do?
Right, good question. In the, no, I think that, no, I don't know that. So in the F table, that's a question that comes up often. After 30 degrees of freedom within, it makes jumps, right? From 30 to 40 to 60 to 120 and so on. You always round down. Rounding down will make it a bit more difficult for us, because the less degrees of freedom within we have, the larger the critical F. Let me repeat that. Remember in the t-table? In the t-table, the more degrees of freedom you have, the smaller the t value. Same thing goes here. The more degrees of freedom within, right? Instead of just degrees of freedom within that you have, the smaller the F value, the critical F value. So we always round down to make our life more difficult. Okay? The ethics of research is always make your life more difficult and not easier. That's just the way it is. So we get this critical value and we compare it to our value. So F, very small compared to the critical F. We need our F value to be larger than this value. Now, based on our calculations, can F be a negative number? No, right? Because, why not? Because we're not basing our obtained difference on a subtraction. We're basing it on a measurement of variance. Variance can never be negative. You can never have a negative amount of variance. So because MSB can never be smaller than 0, you can never have a negative number. All the numbers are positive. So our F is smaller than the critical F. meaning we got a non-significant result. In other words, the p-value is larger than 5%. P is larger than alpha. In other words, the likelihood to get the result that we found, right? Remember, we found a difference of 10 points and 10 points. 170, 180, 100. The likelihood to get this obtained difference by chance is more than 5%. This is a likely result. It is likely to get this result even if there is no real differences, right? In a situation where there are no real differences between wine from the UK, wine from China, wine from Brazil, right? Let's imagine that it's the same quality of wine. There's no actual differences. It's still very likely to find some differences. So it's likely to get this result even if H0 is correct. So because it's likely that there are no real differences between the groups, we conclude there is no difference between the groups in the population. Or in other words, they all come from the same population. Yes?
I do a quick recap just to make sure I got it.
Mm-hmm.
Okay, so our FC, because we only have 2 and 6, which is under degrees of freedom.
Yeah.
For those degrees of freedom, in order to have a significant result, we need to get above 5.14.
Yep.
We only got 22.3, therefore
Yeah.
that's it.
Right. Yeah. Yes?
Again, you said the lower DFSN causes a higher. What is the parallel again? If you have a lower DFSN, then you have a
Larger critical error. Think about the t-table. The more participants you have, the more similar the t-table is to a z-table.
yeah.
And the same thing goes here. The more participants you have, the smaller the f value. Yeah. Right. Right. So think about it. When I say there's a difference between the wine from the UK, China, and Brazil, there's differences between the groups. Right? There could be small differences or large differences. I'm saying I found some differences. How many differences? The variance is differences, right? Think about it. If I say there's variance in our height in this class, right? What am I saying? I'm saying there's differences. I'm different from you and I'm different from her and she's different from her. There are differences. So it is. So the difference between the groups is the variance between the groups. Right? It's the same thing basically. The differences between the meanings is the variance between the groups. Yeah. Okay. So we conclude, because I don't want to step on any toes, that the country of origin does not affect wine quality. From the very raw data from our sample, we got to an abstract conclusion. Right? We took samples, we looked at them, we described them, we used statistics to have an inference about the population. Now, it's not necessarily true. Maybe there are differences, but we didn't find them. Okay? But our conclusion is an abstract conclusion that wine does not affect, that the country of origin does not affect the quality. There are 2 more slides to go. But first of all, does anyone have any questions about this process, about our conclusion? What would happen if our F was larger than our critical F?
There is a difference.
We'd say there was a difference, right? The countries are not the same. Now that conclusion is a bit not really interesting, right? We would need to make it a bit sharper, but that's going to be next week. Okay. So maybe 3 more slides. What contributes to the variance between individual groups? So both the MSB and the MSW can be affected by chance, right? We said MSB was larger than 0, but it doesn't represent a real difference. It represents something that we found by chance. So chance can affect both components. The more noise we have, the larger we expect MSW to be. That's pretty clear, right? MSW is our estimate of variance that is expected by chance. But the more noise we have, we also expect MSB to be larger, right? If there's huge differences, right? If we expect large differences, then a difference of 10 points could be rather small. You can find even larger differences. So chance can affect both MSB and MSW. But if there are real differences, it can only affect MSB. Right? MSW is calculated within the groups. But if the wine quality, the country of origin, really affects wine quality, it can only make MSB larger. MSB won't change. Think about it this way. If coffee makes you less sleepy, okay, giving one group coffee and the other group not getting coffee shouldn't affect the individual differences within each group, right? The coffee manipulation obviously won't affect the control group. So the real effect won't affect MSW. It can only affect MSB. Yes?
The more noise we have, then the larger MSW will be. But the more noise we have, I understand that it can make MSB larger, but it will not necessarily make
Not necessarily. But just by chance we would say
it could be.
Exactly.
Okay.
So I want to transform this formula from MSB divided by MSW to this. F equals real effect plus chance divided by chance. Right? Because MSB is the product of the real effect plus chance, and MSW is just a product of chance. Meaning that we get this. Right? This is just breaking down the same thing. So we get 1 plus real effect divided by chance. Yes?
The noise in MSB would just be like the variables we weren't aware of besides manipulation. It was the variables besides manipulation that we weren't aware of, like independent variables besides. That's essentially like the noise.
Yeah.
And it wasn't just the coffee that was causing arousal.
Yeah, exactly. Could be 1,000 things. We'll get that there when we get to 2N.
The next classic example, more like MSW noise is more kind of like individuals having natural differences and like pest outside differences, like if the pens weren't working or something like that. But more MSB is usually there's noise in MSB is usually just variables we didn't foresee.
I think if you want, we'll like make this the finer point a bit later. For now, we'll just say it's noise. Okay, so do you understand why from this we got this? This is just a development, algebraic development of this. So, if there is a real effect, we expect f to be larger than 1, right? Because if there's a real effect, this should be larger than 1. If there is no effect, right? If this is 0, right, real effect equals 0, then if we sample thousands and thousands and thousands of people, we don't expect f to be 0. We expect f to be 1. The only reason we got f that is smaller than 1 is that because we sampled not a lot of people, right? There's some variance in the sample, and we found a very small result. But usually, if there is no effect and we sample a whole lot of people, we'll get f equals 1. But sometimes in articles, you'll see that, for example, the result was not significant, f smaller than 1. This f smaller than 1 indicates, look, it's such a small value, I'm not going even to bother you with the p-value. Because it's such a small result, it couldn't be significant. So whenever I write in an article f smaller than 1, I'm just saying to the people, look, let's skip it. It's not a significant result. Let's move on. Okay. So whenever you see f smaller than 1, you know it's a non-significant result.
But it's always f equals to 1.
Right, right. So f equals to 1 also non-significant. But if you sample, like, let's say, all the participants in the world, okay, you might get f equals 1.01, which will be a significant result. Okay. So, you'll cover this as well in the presentations. Two more things is, let me just make this go away for a sec. Okay, one more thing. And this is not a big part of the course, but it is a point that is relevant to empirical psychology. Eta squared. Here's a new measure called eta squared. Eta squared is SSB divided by SST. So, remember the pie chart. We're asking how much of our pie is explained by the manipulation, by our effect. How much of the total variance is explained? In this case, we got 7, right? 0.07, 7% of the total variance is explained. Now, this measure is an additional measure to the significance, right? It's obviously related. A very significant result will also have a large eta squared. But significance testing is only part of the information. It's only part of the information. Doesn't tell you everything you need to know, right? If someone tells you, I found a significant result, what most people will take from this, they'll say, oh, there's a difference. But then you can ask yourselves, how big is this difference? So eta squared reflects how substantial is this effect. How much of the variance does the effect explain? For example, there was one example that's relevant from the last few weeks. You all heard there's a new, like the association, I don't know, the cancer association, I don't know what they call it, said that meat causes cancer, right? Meat causes cancer. What do people hear? People hear, if I eat a hamburger, I will get cancer, right? And that's, from a significance testing point of view, that's true, right? Eating meat, manufactured meat, I don't remember now. Processed meat. Yeah. Eating processed meat will enhance your chances of getting cancer. But then you can look at the fine details. The fine details will say, how much more? By how much will it increase my chances of getting cancer? Okay? So eta squared will tell you how substantial is your effect. Now, in social sciences, we don't usually deal with large effects. We usually deal with very small effects, and that's fine. For example, if I do a huge study trying to find a cure for depression, or what affects happiness, and I find that doing mindfulness exercises increases happiness, and the explained variance is 10%. Now, 10% is considered a small effect, but think about it. If you manage to explain 10% out of happiness, okay? If you find 9 more effects like this, you've explained happiness. So 10% doesn't seem a lot, but it can be substantial when we're talking about really large social phenomena. One last slide, 1 minute. Just want to say something that I said throughout the course and just explicitly say it out loud. T-test is a form of ANOVA. T-test is ANOVA. What's ANOVA? Analysis of variance. What's a t-test? It's also analysis of variance, right? In t-test, we look at the obtained difference versus difference expected by chance. What's difference? Difference is variance. So both T and F describe the same thing. So if I conduct an ANOVA on 2 groups, and I'm allowed to do that, right? I don't have to have more than 2 groups. I can